Hi everybody, welcome to a new lecture of ITC 255 on probability distributions, where we cover a couple of continuous probability distributions. Remember that if a random variable is continuous, it doesn't make sense to calculate the probability of each value because there are infinitely many values that the variable can take, and practically the probability of each of those values is nearly zero. Therefore, here we try to calculate the probability that the random variable takes values in certain interval. The first continuous distribution that we cover is uniform probability distribution. Consider an elevator which stops at a floor any time between 0 to 50 seconds after calling it. Then the probability when the elevator will stop has a uniform continuous distribution. A continuous random variable u has a uniform distribution in the interval a and b. Remember that this can be also open interval. Then f of x, which is the probability density function, is 1 over b minus a, with x, of course, taking values in this interval. The expectation of u is a plus b over 2, and the variance of u is b minus a square over 12, and is shown as u distributed uniformly at the interval a and b. Recall the example of the elevator. F of x is 1 over 50 minus 0 is equal to 1 over 50. Now we can use this probability density function to calculate the probability that, for instance, the elevator would stop somewhere between 10 seconds and 20 seconds after it's being called. And then we use the definite integral from 10 to 20 of the probability density function f of x, which is 1 over 50. After some calculation, we'll get 0.2. That's 20%. That means the chance of the elevator to stop between 10 and 20 seconds after it's being called is 20%. The next probability distribution, which is continuous and very much well known, is the normal distribution. Normal distribution is very famous because a lot of natural variables following a near normal distribution, such as distribution of height, weight, income, and so on. Therefore, normal distribution has got a lot of application in probability and statistics. The random variable x has a normal distribution if its probability density function is given by the following equation here, where x is a real number and mu is the expected value or the mean, and sigma is the standard deviation of the random variable x. Then if x has a normal distribution with mean mu and standard deviation sigma, it's being shown as follows. Most of the times it's useful to standardize a normal distribution, meaning that convert its mean to 0 and its standard deviation to 1 by subtracting the mean from the random variable and then dividing it by sigma. The resulting random variable has again a normal distribution with mean 0 and standard deviation 1. In other words, the standard normal distribution is centered around 0 with standard deviation of 1. Suppose x has a normal distribution with mean 20 and standard deviation 5. It can be the age of students at the university. Then z equals to x minus 20 divided by 5 has a standard normal distribution. Then we can calculate the probability of, for example, x between 24 years and 18 years, which is 18 minus 20 divided by 5. So that means we subtract the mean from all three parts here and divide all three parts by 5. With doing so, x is simply converted to z, which is standard normal. On the left hand side, we get 18 minus 20 divided by 5. On the right hand side, we get 24 minus 20 divided by 5, which becomes the probability of 18 minus 20 divided by 5 is minus 0.4, z less than 0.8, which is 24 minus 20 divided by 5. Now we can calculate this probability using a definite integral of the standard normal distribution density function from minus 0.4 to 0.8, which is being calculated in R and turns out to be 0.44. That means the chance that we get somebody whose age is between 24 and 18 If the H has normal distribution with mean 20 and standard deviation 5, it is 44%.